Is it visible?
Yeah.
Okay.
Hmm.
So far, we studied about the ground and reference impedance. You talked like it should be low and it can affect all electrodes. And then we discussed the most important part, which is sampling frequency, or we can call it sampling rate. It is number of data points or number of measurements we collect every second. So for every second, like up to normally we said 250 samples of measurement. So initially we can set it at high.
Yeah.
And you mentioned
Up
that we
to
can
250 means
pre-process.
starts from 250, goes up to 5,000.
Okay.
Yeah. So 250 is on the lower end.
Yeah. Then we can downsample it if we don't need it.
Yeah.
So the sampling rate is usually expressed in hertz, and same as the frequency, signal frequency, that is also expressed in hertz. So example 250 hertz is like 240 times per second we are collecting the data points.
Right.
So the examples you talked about in last class, like if we have 4 measurements in 2 seconds, so sampling rate will be 2 hertz. So if we have 100 measurements in 2 seconds, because sampling rate we always talk in 1 second. So it is very simple that 1 second it will be 50 hertz. That is sampling rate. So in this way
Right.
we can calculate it. So higher sampling rates can capture more detailed information about the brain's electrical activity. So if the sampling rate is 250 hertz, it means that 250 data points. Data points here means the voltage measurements, because it is continuously fluctuating. So therefore there are so many data points we have. So when we set it 250, it means 250 data points or voltage measurements we are going to collect in 1 second for each electrode. So each data point represents the voltage measured at a specific point in time from a particular electrode. So
Right.
this we talked, like here it is very clear that 1 2. So in 1 second there are two times means two data points have been collected. So which is sampling rate is 2 hertz, and here it is for 1 second we can count it, it is 10. So similarly the number of peaks we can see in the both when the sampling rate is 10 hertz and 100 hertz, it is same in 1 second, because which is the 3 peaks. The frequency, signal frequency is same, but the more clarity is here if we see the second one, because the sampling rate, the more samples we've collected. And so frequency, what is frequency now? We can call it frequency of wave or signal frequency. It is also measured in hertz, number of peaks in a second. So in the above image, as we talked, signal frequency is 3 hertz for both, and but more samples give a clear picture of data. So
Right.
for example, delta waves typically have frequencies ranging from 0.5 to 4 hertz. So it's meaning that the wave form repeats its pattern between 0.5 and 4 times per second. Or if a signal has frequency 4 hertz, it means that the waveform completes 4 cycles within 1 second. So if we observe a delta wave with a frequency of 4 hertz in a recording, so it indicates that delta pattern occurs 4 times within 1 second of recording. So normally EEG signals, we know it is a continuous analog signal, and digital systems cannot process discrete samples. So I think that's why we do that Fourier transformation in order to make it simple, and then we do the power spectral analysis
We'll
so
come
that
to
we
the.
can
Yeah.
tell the frequency. So there is a sampling theorem. I studied a little bit about it. So which is Nyquist-Shannon sampling theorem. It simply says that sampling rate should be twice of the frequency.
Or more.
So be at least twice the highest frequency contained. Like gamma is the highest we have. So which starts from the above the 30 and up to 100, or sometimes some people say more than 100 it can be. So
Yeah.
therefore, normally if we want to capture the gamma, we must have at least 250 hertz.
Right.
So
Yeah.
so if we are interested in like the delta waves up to 4 hertz, then we would need a sampling rate of at least 8 hertz according to this theorem. So Fourier, I am not going to delve into it as you will be discussing.
We'll go into it.
Yeah. So number of 10-20 system and 10-10, you talked about like more electrodes. If there are more electrodes in our cap, so we normally, it means that 10-10 is there. And if there are 64 electrodes, it should be 10-20. That's why. So oscillation, we talked, it is basically like the same as signal frequency. The rhythmic pattern is there, repetitive patterns in electrical activity. We call it oscillation, which generates spontaneously in response to stimuli by neural tissue in the CNS. So, but yeah, that is you talked about, means it is basically there is a central value.
So
So
even without a response to stimulus, when you're sleeping,
okay,
then also your patterns of EEG are very rhythmic. It's just a biological nature of the body. Everything works in a rhythm. There are different uh, mm, frequencies of the rhythm, but even without a stimulus, it could be very rhythmic. In fact, in response to stimulus, it could be less rhythmic. If the ERPs will show you a peak right at the onset of the stimulus, it
yeah,
won't be, but the natural things are more rhythmic, like your breath is rhythmic, your heart rate is rhythmic. It's like that. So
but
that's
there
awesome.
is some mean value or the central value is there,
Right.
right? Central value
That's
voltage.
what we call oscillation, goes up, above, and below a
And
certain.
central value, yeah. So EEG recording capture this oscillatory pattern as voltage fluctuations over time. So that's what we measure. So different waves, we know we call it frequency bands, represent different rates of oscillatory activities in the brain, each with its characteristic frequency range. So sampling frequency we can change, but signal frequency we can't. So we know that in medical conditions, specific stages of yoga are there, so the people can alter their frequency, but it's normally it is not possible.
Even with
Uh,
tasks, you can change. So if you start doing something cognitively
yeah,
demanding, switch, or you are
like in
doing
sleep stages, it
emotional,
automatically changes. Yeah.
emotional things you're watching, it will change. So those things will change it. Your behavior will change it a little.
So I wanted to confirm with you in terms of the row EEG. I think it is we see the combined signals. We do not have like delta, alpha. So
Right.
that is the raw signal. So we
Even
call
the
it,
bands themselves are combined, right? The reason we came up with bands, because we don't see one pure signal. We see bunch
yeah,
of different things. So if they are mostly
yeah,
slow waves, we will call it delta. But there'll be a mixture of different types of.
yeah. So by looking at the row EEG, we cannot tell anything actually.
You can tell some things. We'll see.
Yeah. Okay. So a sinusoidal wave often this is you discussed. So it is a sine wave, is a fundamental type of periodic waveform characterized by its smooth repetitive oscillation. That's what sine wave. Amplitude we discussed. So height of the peak. So only the value at the peak, that is called amplitude. So amplitude represented by A determines the height of the wave, while the frequency F determines how rapidly the wave oscillates per unit of time. That is the
Right.
basic difference between this. And this is the sine wave. Like if you see that this is the amplitude, the height. So this is the first, we call it the one full cycle. So like the positive half and this is the negative half. So I think the amplitude can be the highest one, positive one, and the minus one. I'm not sure about it, but maybe it is a plus one or minus one. It goes. It cannot be more than that. I don't know if it is.
It just, yeah, is it the maximum from zero wherever it goes?
Okay. So
If it's symmetric, it will be similar both sides. As
okay.
high as it
So
will
can it
go.
be more than one?
One is just a normalized unit. It could be anything. It's in
Okay.
microvolt, right? So it could be any microvolt. It could be 30
Okay.
microvolt. It could be
30.
150 microvolt. So it depends on actually the amplitude itself depends on the frequency. Delta has higher amplitude and lower frequency, and the gamma has much lower amplitude and higher frequency. It's just it's an observation. It's an empirical observation. That's how our brains work.
Okay. Thank you.
It's called the power law.
So, okay, let me come to that. I'm sorry, my that Anaconda was playing up. So I just tried in the R, and it is working here as well. This is let me show you just the wave I created. This is the frequencies for example, this is a sine wave frequency we are taking here. Like four peaks are there.
Right.
Amplitude is one.
Hmm.
Phase is by default it is zero, or we can select it some if we have. And
Hmm.
the duration, like I stopped EEG just after 2 seconds. 2 seconds I recorded. The
Right.
sampling rate I am taking 250. So then the time I have generated, like from zero to the duration, which is the, for 2 seconds. And we know that if you multiply duration to sampling rate, means 2 seconds into 250, then we will have the total samples we've collected.
Right.
So I've created that now. And okay, so this is the sine wave formula. We know amplitude sine 2 pi, frequency into time, and plus phase, which is by default zero. And I've created as a data frame. Now this is the uh,
Are you sharing the screen? I can't see it. I can still see
okay.
the.
Oh, sorry, I'm sharing it. Is it visible?
Yeah. Yeah.
Okay. This is the frequency for amplitude one, and phase 0. So duration I recorded for 2 seconds EEG, and the sampling rate I am taking 250. 250 times, and this is a time sequence I've generated. Means I started from 0 and duration up to 2 seconds, and it is duration into sampling rate. We know by if you multiply it, we will get the total number of observations we collected in 2 seconds.
Right.
So which is 250 into 2. So then the sine wave formula, amplitude sine 2 pi, frequency into time. So and this is data frame I created, and then this is the graph now. What happened? Yeah. So because it is 250, so this is very clear now that there are in 1 second, if we count it 1, 2, 3, and 4 peaks are there, and that's what my frequency is. So if I take it like here, the one which is uh, not actually right, this is a problem. We call it aliasing occurs. So aliasing is something maybe the error type which we talked in that here. It's not according to that theorem because it should be twice to that frequency. It should be 8 at least, so that if I keep it 8, let's see what happens. So this is the sampling rate 8, and by 8 this is what comes. It is nothing is clear here. Yeah, 8, I think we can count it. It's in 1 second. Like it should be the 4, 1, 2, 3, 4. But ma'am, it is showing like -4 and plus here also 4.
Yeah, there's
Something in
something
one
wrong
second.
with this.
Yeah, I think so. Maybe okay. Let me.
Uncomment the upper one.
Yeah, that's what happened. This one, I think.
But I don't think that should matter. You should reinitiate that variable.
Okay, let me start it. Frequency. Yes, same. So
Yeah.
if we take it like 100, then it should be, I think, more clearer now. Yeah, it is 100. 100. It gives a clear picture.
Yeah,
So we
we
can
will
count.
use line points to plot. Na? It's just instead of just dots, you connect them with lines also. How will you do
Yeah,
that?
we can do that. Yeah, we can do that. I
Okay.
remember that feature, but it will take time. So I think it is clear. I'll do it next time.
Yeah, do it next time so then you'll see exactly the shape. Otherwise, it's just sometimes harder in the scatter.
Yeah, but if the sampling rate is very less, then it is very difficult. Like in the
So make
50,
it
maybe it's not
so
possible.
let's do here only. So keep the sampling rate high, make it something like 500. Let me show you the effect of the phase. So make it 500, the sampling rate. Yeah,
Okay,
it's very hard for you to tell now which dot came first. So that's why you do line points, it will be easier.
this is, yeah, 5.
Yeah. And then make frequency to 2 so that we can clearly see it. Yeah. Plot it. Now you have a phase of 0, right?
Yes, yes.
Make it pi by 2.
How to do it?
So you have this pi, right?
Yeah, it is PI.
Yeah, so just pi divided by 2.0. Make in the phase upper you have phase, right?
Okay,
Yeah. Here.
yeah,
Instead
here,
of 0, make it pi by 2.
here I should pay by 2.
So amplitude and frequency are very clear to you both. So we'll just move to phase. Phase is little more complicated than
Like
that.
this, ma'am, it is pi by 2 something.
Yeah. Now run it. Can you keep both the plots? No.
Uh,
So did you see what changed?
Pi by 2. I didn't notice it properly.
Make it
So,
0 again.
yeah,
Make make it,
just
make it
one comment. Yeah, that would be better.
Can you do two plots together? No. So let me now go to the
So
notebook.
this
So
is
I,
when I think it is 0. Yeah, the pi phase is
I
0.
didn't understand what happened, right? So let me go to the. Now you can stop sharing. So this is good. You can play
Okay,
around.
sure.
Next time you can play around with the phase also. So let me, because phase is like a little complicated than frequency. Frequency is very simple. So you've already understood that well. I'm not going to go. So you understood the signal frequency.
Ma'am,
Um,
I don't know the phase actually. I just know little bit that is by
So
default it is 0
we'll cover
something.
that today. We'll cover that today.
Okay.
Other thing to notice in terms of signal frequency is When you have higher frequency, that in terms of just, what does it correspond to in terms of your brain state or your mind state? Normally, low frequency refers to signals with fewer cycles. So you understood that. It actually is linked to more relaxed states. So when you're more relaxed, for some reasons, the frequency that your brain generates in terms of the voltage is lower. When you're more aroused, you're more engaged in mental activities, for example, solving a puzzle, your oscillations would have higher frequency. Okay, so that's something that we observe in people. When they are more aroused, more alert, more awake, solving problems, they exhibit higher frequency. And when they are drowsy, meditative, sleeping, they exhibit lower frequency. So frequency is very important. It helps you sort of characterize which state someone is in. Okay. Um, this is the original paper. So here also I wanted to show that. So there was a guy, right, back in 1929, he published the first paper on EEG. What he observed was, he said there are two types of waves we observed. One can distinguish larger first order waves with an average duration of 90 milliseconds. So you can convert this into frequency. Okay, he says one duration of one wave was 90 milliseconds. So frequency comes 1000 millisecond by 90 millisecond. It comes around 11 hertz. Okay. So because he observed this, he called it alpha wave. Then again, in himself, I think he was doing the experiments on himself. And then he also observed another frequency, another type of wave, which had an average duration of 35 milliseconds. This is why you need to know different types of nomenclature, not just one type, but multiple type, because people will write it differently and you'll get confused. So then he noticed another smaller means lower amplitude, second order waves of an average duration of 35 milliseconds. So second wave ka frequency becomes 1000 millisecond by 35 millisecond becomes around 28 hertz. So then he called this one alpha and he called this one beta. Alpha beta just means first and second. So you observed this first, so you called it alpha, and then you observed the second, called it beta. So these are the most dominant waves you will see in humans and also other animals, not just humans. Most animals will also exhibit very similar frequency ranges. Okay, so these are very biologically also interesting frequencies that you observe. And based on this, you can decide your sampling rate, alpha, beta, like you said, right? So then he says what? These are actually from his paper. He called the large amplitude rhythms, approximately 10 hertz. It was induced by eye closure in the awake, calm subject. Subject is awake, but eyes are closed. He called it the alpha rhythm because he observed this first. Then he named the faster, smaller amplitude. The higher frequency beta had smaller amplitude present when the eyes were open, beta wave. Okay, so these are the first things published in first paper, first EEG paper. This is the guy who came up with the EEG. So this we have talked about. Now EEG, we know now that it's not singular frequency. It comprises of multiple frequencies together. We'll see how that looks in a plot. So to simplify that for analysis, we sort of came up with the bands that if it's a mixture of something between 0.3 and 4, we'll call it delta, but it's still a mixture. And this also helps us to categorize brain activity in broad states. So again, like deep sleep meditation. So it helps us. It's a biologically relevant category. So that's why we do it. So now we'll go to amplitude. You've understood. If we increase the amplitude, so here amplitude is half, here it's 1, here it's 2. Frequency is the same in all three, right? You can see that. In 1 second, we still have only one wave. But all we are doing is changing the amplitude.
Ma'am,
Okay.
so the frequency bands we have like the gamma, beta, alpha, delta. So they are also like we can talk in terms of amplitude and frequency. Like if I'm saying that amplitude is like the frequency is lowest and amplitude is highest. So which
It is
means the delta.
generally seen like that. So it follows something called a power law. Higher the frequency, lower the amplitude, lower the frequency, higher the amplitude. We see that, but there are exceptions. There are peaks and there's some other behavior. So that's
Because
what
in
we
the
thought.
one of the paper I've seen that like people have mentioned that lowest frequency highest amplitude and then they mentioned delta waves.
Right, right. So delta waves have very high, huge amplitudes. That's why we plot it in a log scale and we'll see. So when people plot power, power is just amplitude square. So that's
Okay.
what people are interested in. We want to know which frequency had how much power and how is it changing as you do different things. So that's what people are interested. That's why I was saying, if you understand these three concepts, phase, amplitude, and frequency, you basically understood EEG. That's all there is. Now only requirement is to understand how these change as your brain behavior changes. That is a research part, but just fundamentally, what does these signal mean? They just mean amplitude. A wave is basically characterized by frequency, amplitude, and phase. So we'll come to phase. So signal amplitude is related to power. So when we talk about any brain state, we'll talk about its frequency or frequency range or frequency band, and we'll talk about its power or amplitude. Why is it important? So higher amplitude are associated with stronger or more synchronized neural firing. Even if so two people are showing delta, but if one person is showing delta with higher amplitude, we are saying that their brain is likely to be more synchronized. Their neurons are doing more similar things as opposed to not. So both things are important. So it's like, how many times am I punching someone and how hard am I punching? Both are important, right? So it's like that. Both things are important. Uh, Amplitude can differ across frequency bands. We discussed that. It's typically called the power law. Why it exactly happens? It's a big open area of research. It's not fully concluded yet. Amplitude variations can indicate again. It also indicates things which are relevant to brain states. It can indicate changes in your cognition, alertness, abnormalities as well. Like in epilepsy, a lot of people will have they will also exhibit delta, but maybe even much higher amplitude than normal people. So it also helps you detect like biological anomalies. Now coming to wave, so you could understand what phase was doing, right? So what is the difference between these three curves? Is there any difference in frequency? You mute.
Yeah, sorry. So it's not clear. I think the last two, because peaks are not visible completely, but in the first one, it is bit clear that there are two peaks.
So you don't have to start from zero, right? You can, if you started from zero, and so you can let's say you start from 0 to 1, you can't tell, right, exactly, but if you took a longer time interval and then you can count in 10 seconds how many peaks are there. So the idea here is the frequency is the same. In 1 second both of them have two peaks, one peak, one peak.
Yeah,
This
one peak is, yeah.
also, and there's no difference in amplitude either. They
Remember,
are
in
all,
the third one, if we see, it is that in the 1 second, there are two peaks because
yeah.
one is
What
at the
if I
two
take
and one
one
is at the
second? What if I take 1 second from 0.5 to 1.5? How many peak do you see in 1 second?
0.5 to, and then it is one peak.
So okay, so frequency is identical. Here again, you can take an interval from point here to here, and you'll see in 1 second there's only one peak. So what is the difference? And then the amplitude, everyone is going to 2 maximum and minimum -2. So the amplitude is also the same. What is the difference?
And then why are we counting like the peak at the top? It can be the peak like the what it is showing in the third one, 0.50. That is also the peak. If we just take it 0 to 1 second, if we look at it, it is there is one peak, but it is downside, means in the negative part.
Amplitude you can take as an absolute value. What is the maximum value? And if you consider an oscillation, the idea is behind that it is symmetric. Up and down, it goes about by about the same time, same
Yeah.
value.
So the downward also we can count as a peak, as a frequency. That's what I'm
Yeah, so
saying.
that's also going to only -2. No, here only it's going to +2, -2. So there's no difference in amplitude.
Yeah, no difference. It's equal. Yeah.
Yeah, so what is changing? We're just shifting it. That's what's changing.
Yeah.
Yeah, so that shift is called phase. So one way to think about it is at t equal to 0, what is the value of your wave? Here
Okay.
at t
T
equal to 0, your value of the wave or the
zero
signal value is 0.
zero.
Here
Yeah.
at t equal to 0, it's something higher. Here
Okay.
at t
Yeah.
equal to 0, it is actually the highest.
Yeah.
And it can go from, so then it's actually, it goes from 0 to 2 pi. If you make it 2 pi, the phase if you make it 2 pi, it basically goes to the same pattern. If you make it pi, it will basically flip. I'll show you in the notebook.
Okay.
Yeah, so it basically is like where how much are we shifting it? If you completely shift it by one cycle, it becomes the same thing. But if you shift it half a cycle or quarter a cycle, if you shift it half a cycle, this is quarter cycle. So it basically went from here, we shifted it to here. So that's why it's zero. This has the maximum value and this has the minimum value. Okay. And you can keep shifting it. So you can try out different values. You can later on also try. So phase is also very important. Three things are important. Amplitude and frequency you understood. This is phase. So what it means is if I have let me think about an example. Um, trying to think of a normal example. So every country has a 24-hour day, right? But India's morning and London's morning, like UK's morning, is a different time. So we are shifted in wave. We have the same frequency of days and years and everything. And we also have the same amplitude if you consider some kind of temperature or whatever. But what we are shifted in is time. So when day happens in India is different from what time day happens, but we are following the same 24-hour cycle. So phase is something like that. You're thinking about how much shifted are they. And this is important in understanding various things. Phase synchronization is very important. If they are all going up together and down together, even if they are different in frequency, that could mean something. How aligned are your left and right hemisphere in terms of phase? That would be interesting. It can also tell if you gave a stimulus, which waveform started first and then which followed later. So it gives you some idea on what is happening first. For example, in case of I think in case of theta wave, they see that it starts from hippocampus. There the phase is zero, and then somewhere else it's a little higher. So that way you can tell what started, which area of the brain got excited first. So those things come out of phase. So it's little more complex, but if you play around with the code, you will understand it. So I'll show you how to do it in the code. Um, uh, so my notebook is visible or still the presentation?
Still presentation visible.
Okay. So you're also playing around with this. So now let's make the phase. So this is phase equal to zero. Okay, so there's nothing added here. Let me do plus phase. That's why I moved to this because you can see both the plots together, right? So this is phase equal to zero, which means at zero, this is zero. Now if I make phase equal to, let's do small number, pi by 8. So it shifted a little bit, see? Yeah, we can keep going. I'm not changing anything. The signal frequency is still 1 hertz. The amplitude still 2. Only thing I'm doing is changing the phase. I'll just change the phase now. These are still the same. And I'll change it to pi by 2. Can you see now? And let's make it even higher. So we'll make it 180 degree. Making it pi. So it will just flip. Okay. Here it was 0. Here also it is 0. But then from 0 it goes to positive direction first and then negative direction. So it's almost like you've shifted it here at t equal to 0. So that's a phase difference of pi. Okay. And then if you make it 2 pi or a multiple of 2 pi, it basically repeats itself. So if you make it into 2, it becomes the same thing. So 2 pi phase difference doesn't mean anything. Just basically you're shifting it by entire cycle. So you guys play around with this. Okay. Play around with this, see what it's changing is basically shifting it, moving it spatially. Okay. So it's a coding exercise. Do it in a coding fashion. Now this much I think is clear. Now one more thing I'll show you. This is something you can play around with. Now let's look at mixture. So you have this as y1. And then I'll make another wave. I'll call it y2. I'm not changing the phase here. I'm just changing the What should I change? Changing the frequency. So this one had a signal frequency of 6. This one had a signal frequency of 1. And because this is 1, I'll change the amplitude here. Y2. So this is a mixture. What did I do? I took one wave and I added another wave on it. So this is what a mixture looks like. Let me change the range here. Okay. So if you mix two types of waves, so basically you have a larger frequency, smaller frequency wave, which is like a delta, more like a delta. And on top of it, I am adding a smaller frequency wave. So this is what it's going to do. You can keep playing with it. You can change the amplitudes. Um, you can change the frequencies. You make it 10. So you understand, this is just getting added up. So that is what more like that is more like an EEG signal. And it's not even just one or two, it could be multiple. So now it becomes very challenging and it'll look really weird because you will keep adding multiple 4, 5, 6. They're not pure frequencies either. So you have to like add, let's say one, let's do one more. 3. So that's why you need Fourier transforms. Come to that. Make it. Let's make it delta. Let's make it
It's
gamma.
slightly difficult to comprehend it
Yeah.
comparatively, the frequency and sampling.
What I'm doing is, let's say this is a signal frequency of alpha band, okay? And I've given it an amplitude of 0.5. Then I created another signal frequency in the delta range where it's 1 hertz. And then I've given it a higher amplitude. Okay. And I'm creating a combination of the two. So that was a combination of those two. That was a combination of those two. Now what I'll do is, so this is your alpha plus delta, someone who
And
is
why we are making it complicated by adding so many ways?
because that's how your real EEG data is, no?
Okay.
This is still much simpler. Your EEG data has multiple similar ones, then multiple different ones. Then each channel would be a combination of different ones. So that's how your real
Okay.
world data is. You're not
So
dealing with
it's
science.
not according to like the number, like if I have 64 electrodes, so which means 64 waves. It's not like that. There can be in each electrode, there are number
Even
of signals.
Yeah, even this is too simple. EEG data doesn't look like this. This is simple. This is still two sinusoids. One that is not a pure sinusoid, that there is a mixture of multiple types of waves. So if you don't understand mixtures, then it's difficult. So this is the only thing, like, now you have to understand that it is superimposing different types of frequencies. And
Okay.
in most cases, you will have multiple, some power in each band. What does that mean? It means that each of your channel is comprising of signals of different frequencies together. And they have different amplitudes also. So that is why we do a power spectral analysis. We look for how much amplitude was there in each of these frequencies. That is exactly what PSD is. And Fourier transform is a way to do it. Okay, so let me show you one more example, and then obviously you can take some time with it and play around and stuff. I'll share the notebook. So this was alpha and this was delta. And then similarly, you could do alpha and then you could do gamma. So alpha was 10 hertz, this is around 30, let's say, and the amplitude would be even smaller. 0 point, let's do 0, 1. Y1 plus Y3. It's too small to see. Yeah, you can't see it. You need even better sampling rate to see gamma. That's one of the problems. So alpha beta you can see, you can make it 16 or something. Now see how it becomes. So these things will all matter. What are you doing? What kind of frequencies are you adding up? What are their respective amplitudes? So all those things become important. So now you have to learn about what's called a Fourier transform, because looking at this, I can't really tell what the hell is happening, right? What is this? What is this? Here you can still say, okay, I see two big waves in a second. So this looks like there's some kind of delta. Then you can count these smaller peaks. In 1 second, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12-ish smaller peaks. So it looks like it's two types of frequencies going on, but it will become more and more and more complex. So you need some mathematical tool to be able to do that. So in this function, I have created one more thing. So along with plotting the time series, it will also plot what's called a Fourier transform. Fourier transform, what it does is, then we'll go systematically. Okay, so we have some time. Okay, so Fourier transform decomposes your signal into the frequency and the amplitude. So it will tell you what amplitude was there in the wave. It's a mathematical thing. It will tell you that. So let me do this. So here you can see the plot. It had 6, signal frequency was 6, amplitude was 2. And I do this again. Now I'm plotting along with the signal, I'm plotting the Fourier transform. So what is Fourier transform showing? It's showing that nothing, nothing, nothing. There's a big peak at 6. So it's a mathematical framework of telling you your signal had a peak at 6, which means the frequency in your signal is more likely to be 6. So it tells you that. If you give it a signal, it will tell you what the frequency was, the prominent frequency was. If it's a pure signal, it will give you higher, more sharper thing. But let's just say that this is a magic box. You throw it a signal, it will give you the frequency. Okay. And here it will give you the amplitude in some form. It gives you power. It can give you power. Power is basically amplitude square, absolute value of amplitude square. So it will give you power and the frequency. Now let's keep doing that. Let's see if it does that. So here it gives you, we had used a signal frequency of 2. Here is giving you peak at 2. Okay. So it's a magic dabba. You don't have to go through the maths of it. Just understand that it's an amazing tool. Some mathematicians have discovered it. We throw it away, it will give you the frequency. It's just like that. Beyond that, we will not go into the maths. It's a abstract type of maths. Now we've given it a signal frequency of 1. It's giving you a peak at 1. Okay. So it's a very good tool for complicated combination waves. We'll throw it the mixture also. We'll see if it gives you the mixtures. So far we had thrown it a 1 wala wave, right? So it's all giving you the frequency. Now here we were changing the amplitude from 0.5 to 2. Okay, so it will also give you the amplitude ka difference. So here 0.5 wale mein it was giving you here the amplitude of 150-ish. Here is giving you 450. So because we made it higher, it's giving you a higher value here as well. So it gives you both peak at what frequency is your prominent frequency and how much power was there in that frequency, both things, or how much amplitude, highest amplitude it goes to.
Power is amplitude is square.
Yeah. So same things, if you increase the amplitude, it will increase the height of the peak, and frequency is in the x-axis. Okay. Keep doing that. If you change the phase, nothing changes in this construct. So it doesn't give you any information on the phase. It will give you the same result every time. Okay. So this was a different phase, this was a different phase, this was a different phase, it will give you the same. So it doesn't consider different. So for phase analysis, we have to do different kind of analysis. Just Fourier transform will not give you the phase, it will give you the amplitude and the frequency. Now in this, you already knew what the frequency was. So it's not doing anything special. But here, for example, here you don't know what the frequency was, right? Like it's looking very complicated. Now Fourier transform will give you two peaks. Is giving you one peak at 1, I think 1 is what we used at 1, and it's giving you that at 1 frequency, the amplitude is much higher. And it's giving you another peak at 10, and it's saying at 10, the amplitude is much lower. That's how we had constructed this wave. 1, we had used an amplitude of 3. At 10, we had used an amplitude of 0.5. Okay, so it's able to tell that. And if I give it 50 also, it will give you 50 answers. If you had 50 summed up 50 different frequencies and amplitude wale waves, it will give you the decomposition of that. So now it's so much simpler. You can tell that, okay, my waveform had only two prominent frequencies. And then this lower frequency it had higher amplitude and this had lower amplitude. And that's how basically you will do most of your EEG data analysis. You'll do some kind of Fourier transform, slightly more difficult construct, but broadly the same. And we'll use libraries to do that. And so here also, now here is so difficult to tell from the naked eye. It will give you the answer. So now it's telling you there's a peak at 10, which means one of the frequencies is 10, another frequency is around 16 or something. So 16 is what we use. And this had higher amplitude and this had lower amplitude. Okay, and we can throw it as many combinations. You can do y1 plus, it's to that. So that's why Fourier transform is really, really useful. Whoever came up with that, it's made our life simpler. So now I've made three waves here and I've given it to that dabba. Now it's creating three peaks, one at 1, 10, 16. And it's also showing me that amplitude here was higher, here it's lower, here it's even lower. So that's all there in EEG data analysis. You will have frequency here, you will have amplitude here, you'll keep making plots. Okay. So far, this much you spend time, play around with it, understand, clear your doubts like you did today. I think that's about it. And then we'll move to the actual EEG signals. Because maths-wise, there are only three things. Amplitude, frequency, phase, understand those well. And then you're dealing with mixture. Understand that you're dealing with mixture. You're not dealing with one wave, you're dealing with a combination. Because you have what 80 billion neurons. They're not all doing the same thing. Some are helping you keep your respiratory things going, some are doing something else, some are doing something else. You can't expect them all to be aligned and produce like same kind of waves. So they are all doing different things. And for 80 billion
If
neurons,
they create the same, it would be easy for us.
yeah, it would be like music, right? But that they do that somewhat in the sleep stage. They are doing
Yeah.
mostly the same thing, but not completely. So you'll see more of combination of delta and stuff. We can get into that as interpretations of these waves. What do they mean if you're interested? But mostly this much analysis part you have to understand so that you understand when you're doing a result, what is it that you're presenting, that much is important. And the other important part is then statistics. This was all signal processing. If you have a rhythmic signal, what are its three qualities? Its three qualities are phase, amplitude, and frequencies. And what happens if you combine the signals? If you combine the signals, what is the tool that we use to understand its properties for a combination signal? That is Fourier transform.
Fourier transformation.
That's it.
It gives the Fourier transmission basically in terms of amplitude and frequency. We can get the
Yeah,
waves.
you can get the amplitude and the frequency back from whatever wave you threw in.
Okay. Ma'am,
Yeah.
could you please shed a light on like how the EEG data is discrete data? Because I studied about discrete and continuous, but I have seen that there are two types of Fourier transformation, which is the one is discrete and one is the continuous. And normally it is said that EEG data is discrete data because it is a particular time we are recording it. But how we can say that it is discrete? I think it is continuous data.
See, your brain is continuously producing things. You can't measure it continuously, no? So you can only measure it at different intervals. So the moment you are measuring something at different, which is how everything in life goes. Whenever there is a measurement, you can only do it in a discrete fashion. You can't measure something continuous. So continuous things are part of theory and discrete things are part of practical life. So Fourier transform has two different mathematical formulas. If you had, let's say, y equal to x square,
Mhm.
so that's a formula. That's a theoretical formula. Then the
Which we
Fourier,
cannot use in reality.
that's a formula. So you theoretically you can derive the Fourier transform of that formula. But in real world measurements, you're only dealing with something that was collected over time. You don't have a formula for it. So then the Fourier transform formula itself changes. It is a summation formula as opposed to an integration formula. So it's a maths.
So, ma'am, like that, I think whatever we collect the physiological parameters, for example, HRV, blood pressure, they all are the discrete data, not continuous.
Every measurement is discrete. It can't do continuous measurement. We call it continuous because it seems like we're collecting at regular interval, but continuous in our sense, it just means regular interval,
Yeah,
nothing else.
that's what.
So you don't have to worry about continuous. Okay, so you only, if you're reading, you can just read about the discrete Fourier transform,
Okay.
because that is what we are practically going to use. And I don't think you need to get too much into the maths. It is a summation e to the power minus I x t
No,
dt, that
I
kind
don't
of
need that. The
thing.
programming does it quickly, so I don't need to delve
But
into
then
it.
the continuous one is needed for if you say dealt with just sine x. So you know sine x has a property, and then you do integration of sine x, you'll get cos x, those kind of things. So those are continuous things, but the data we collect is only discrete. It's always going to be discrete. So you can focus on the discrete part. And then how, so this is one type of library that I use. So normally you will always use a library for Fourier transform. See
Yeah.
how simple library is. This is, I'm saying if plot FFT is 1, so which means yeah, I didn't want to plot it early on to confuse you, but now I put it 1, so it's always going to plot it. This is just one line of code. Where is it? FFT of Y. That's it. It does everything for you. And there's a way to get help. So this is a library from NumPy. There are different libraries for MNE, Python, for EEG. We'll use something special because this is going to be a little slow. So we'll use a different library, but the idea is you don't have to worry about how it's doing that. You will worry about some of the parameter that you'll just mention in the methods paper, that what kind of Fourier transform was used and what kind of, so it uses a sliding window Fourier transform because you're dealing with so many frequencies, not one or two. We are basically, we are going to plot everything from 0.1 hertz to 140 hertz and power in all of them. So because of that optimization, we might use a different library. Another thing I wanted to show you, if you want help, you just put that function and put a question mark and click. That will give you the help. It will give you
Yeah, it
the
is same as R. Yeah, that's
so
what.
it will give you that help, and then you can see the default option. That's all you'll need in life generally. That what were the default options when I did something, and that you have to pay mention in the paper.
Yeah.
But this much is enough for just the signal part. This is how we deal with a signal which is rhythmic oscillatory in nature. These are its various properties, and it will be real world signal is always going to be discrete and it's going to be mixture. So we need tools to decompose it into useful things, which is Fourier transform. So that's about it. So I'll stop here. There is a summary, right? So if you change the amplitude, the value at the peak changes, but the frequency does not change. If you
Yeah.
change the frequency, number of cycles in a second changes, but I've not changed the amplitude or the phase here. So both are starting at 0, going highest at the same point, which is 1. So I'm only changing the frequency here. Here I'm changing the phase. So it's basically just shifting the signal. Okay, so here the amplitude is the same, the frequency is the same. I'm just shifting it. So at 0, this was something else. This was 0. This was something else. That's all we're changing. We're just shifting. Okay, and here in real world, everything will be changing. It will be a mixture where we can change amplitude, frequency, and phase. All of these things will be changing, and your brain would be generating things at different frequencies, different amplitudes, different phases. So we do analysis to sort of decompose them into their right constituents and look at those plots. Yeah, so this we've done already. So this is the same thing. This is a pure wave. It will give you one peak. If it's a mixture, you can't really tell what is happening here. The Fourier transform will give you the actual frequencies of the prominent waves and also give you the relative amplitudes. So that's about it.
Ma'am, in the next class, you can talk about like I tried to study about the EEG data, what we get from the raw EEG data, the formats of that. Like we have in different formats. So there are so many numerous formats are there. One of them is CSV file, which is very common, but I don't think we use the comma separated.
Yeah, so there are libraries to handle each of them. The most
Okay.
common one is EDF, European data format. So next time we will
Yeah,
use,
EDF. I think that is the most common we
that's
get.
called European data format. With brain vision, it will be something else.
Okay.
So brain vision is not EDF. Brain vision is brain vision's format. So we use a library which is for that particular data format.
Okay, or we can convert that. I think that would be very
Yeah, so
difficult to
each of
convert.
them will just change the first line of the code, how you load. So which
Okay.
function are you using to load the data? We'll change that.
Mhm.
Shilpi, I have a question for you. So you shared the raw data. The raw data itself, there's some problem. Let me bring it up actually.
Yes, ma'am, please.
Yeah, so it's still showing me a frequent sampling rate of 1 hertz, which cannot be how it was collected, because the paper was saying it should be collected 256 hertz. 1 second. Yeah. So
Can I share?
yeah. You can share. I also have it. I've downloaded it. Yeah, so I got it. So you can check your CSV file that you again shared is a CSV file. Normally, what I've seen in my experience, uh, raw data is not in CSV format because CSV is a high memory format. Normally, it would be EDF or FIF or something else. My entire screen. So this is your, let me share. So this is what you've shared with me. So you can see the timestamp here.
Yes, ma'am.
So it's showing here. See, so it's showing the date. And it's showing
Mm-hmm.
10 a.m., 27 minutes, 07 seconds. That's your first sample. Then your
Yes.
second sample is 08 seconds. So each second you are having only one sample.
Mm-hmm. Yes, ma'am.
So that is not EEG sampling rate. It's not, you can't say that your sampling rate was 1 second. This is not the raw data. That is one problem. So here, 1 per second, you can't even see delta. How will you see gamma and all? So it is synthesized data. That is one thing. The other thing is you're seeing this delta alpha. So someone has processed this data and already given you either this is probably power in this electrode and the delta frequency band. So someone has done that band passing filtering frequency analysis and given you most likely it could be power. I'm not sure. So if you're going to use this as it is, you have to understand what is it and who did and how they did it.
ओके मैम बट मैंने इसको डायरेक्टली डाउनलोड किया है मतलब ये
So
किसी
directly तो
थर्ड
maybe
पार्टी से नहीं
Muse,
लिया मैंने.
Muse might be giving you both options. Otherwise, how research people don't download these kinds of. This is good for it might be displaying on the screen. Um, so if you can't locate the raw data, you have to go over Muse bands manual and what is it that it's giving? Is it amplitude? Is it power? It's already done the analysis for you. Okay, so there's not much I can explain here because it's already done. And I don't even know what it is done. So it will be very really difficult to write a paper if you don't know what that they have done here.
That's good apparatus if it is giving like directly power. You know?
Yeah, but that's not good for researchers. If you're getting directly HRV and they won't tell you how they calculate the HRV, you can't publish in any good journal.
Yeah,
You have to exactly explain how did you do the calculation. Otherwise, how will people replicate it? So you have to
exactly.
figure out.
इनफैक्ट मैम म्यूज बैंड ना कुछ एप्लीकेशंस के थ्रू में इनके डायरेक्ट ग्राफ भी जनरेट करके दे देता है और रिसर्चर जस्ट उस ग्राफ को एक्सप्लेन करते हैं. उसके बिहाइंड थ्योरी को कहीं भी एक्सप्लेनेशन मुझे नहीं मिला म्यूज बैंड के थ्रू.
बट उन्होंने तो लिखा है कि 256 हर्ट्ज है सैम्पलिंग रेट. तो उनको पूछो 260 हर्ट्ज वाला सैम्पलिंग रेट का डेटा कहाँ मिलेगा. कैन यू आस्क समवन. डू यू हैव अ वेंडर यू कैन आस्क.
ओके मैम आई विल ट्राई.
अब वेंडर को पूछो कि इसका मुझे रॉ डेटा चाहिए 256 हर्ट्ज वाला जो बेसिकली हर सेकेंड में 250 सैंपल दिया हुआ होगा. दैट इज व्हाट वी वांट. एंड अगर वो नहीं मिलता है सिर्फ यही ऑप्शन है हमारे पास तो ये कैलकुलेशन करने का तरीका क्या था. कौन सा स्पेक्ट्रल एनालिसिस का कौन सा तरीका यूज किया गया था वो बताइए. और ये बताइए कि ये सब जो चीजें हैं ये क्या चीज है. ये पावर है या ये एम्पलीट्यूड है या क्या है.
ओके मैम.
The problem is you can't do any analysis on this. This is one sample per second. You can't do any spectral analysis on this data. क्योंकि बहुत बहुत ज्यादा लो फ्रीक्वेंसी हो गया ना. क्योंकि अब मैं इसमें तो वेव्स ही नहीं बता पाऊंगी. तो उन्होंने ऑलरेडी सब कुछ कर के दिया है आपको. So to figure out what so normally in MNE you'll know exactly which method you used for spectral analysis. Multi taper था या वेल्च था. So those are different ways of doing spectral analysis. You have to mention that in the paper.